Hello friends, I'm Ashish Darbari, founder and CEO of Aximize. To our new listeners, welcome, and to our old ones, welcome back. Today I have a very interesting personality in-house, someone who is a key influencer in the RISC-V ecosystem and is a senior director of next generation platform technologies at Western Digital, and his name is Zvonimir Bandic. Welcome, Zvonimir. If you don't mind, can you share a bit about your personal history? Where were you born and how did you get into science and engineering? And how exactly did you end up at Western Digital?
Well, I was born in Belgrade, former Yugoslavia.
Oh, wow. Okay.
I have gotten interested in science and engineering kind of early on, or around the age I was 13 or 14, when I realized that I was not going to have a great career as a violinist. And in Yugoslavia, these science and math programs for kids were really, really very well organized. There was all sorts of competitions, science camps, specialist schools and stuff. So I kind of took that path and participated in a lot of math and physics competitions, and ended up studying technical physics in the School of Electrical Engineering. And then after college, I went to California, to Caltech in Pasadena, to pursue a PhD in applied physics. So my passions were around semiconductor devices and a wide bandgap semiconductor electronics while at Caltech. But when I graduated, there were no jobs in what was the beginning of the gallium nitride power electronics. So wow. that actually the technology became commercial only like last year.
Right, yeah.
And I was actually the very first person who built a gallium nitride power high voltage diode and high voltage transistors. But now you can actually, I think most of the consumer electronics will transition to gallium nitride based chargers, and I think it's going to be a big hit for electric car charging as well. So
yeah.
But back then the jobs on gallium nitride were only, I think, maybe a few jobs on the East Coast and academic jobs. So I interviewed with IBM Research and got the job in IBM Almaden Research in storage research. And I'm still in that same job, still with the same badge number, because IBM and Hitachi made a joint venture called Hitachi Global Storage Technologies that became AGST and eventually got acquired by Western Digital.
Oh, wow. Okay.
So I never actually spent 21 years on the same job, basically.
Wow. So quite a journey, hey, from physics to landing up a job in storage. And who would have thought a storage would be a big deal 20, 30 years ago, right? I mean, of course, it has been an important, but people were only talking about clock cycles and Moore's law and processing power, not thinking about cloud computing, were we, back then?
It definitely was a big deal in 1999 when I started. People in storage realized that they were on the cusp of what they can do in terms of areal density. And there have been a number of challenges overcome in magnetic spinning disk devices to reach the density where we are today. And in 2003, we realized flash becomes another challenge. And actually, in my first 10 years on the job, I was still mostly in the physics world, focused on a variety of the physics and mechanics problem in the HDD. And it's with the emergence of the flash and especially phase change memory that I started sort of converging more towards electronics and hardware design.
So I work in digital.
As it goes in experimental physics, you get so much training in how to build your custom measurement tools, how to design a software stack, and how to build things from the scratch. That departure is relatively natural for people in experimental physics, and my college training was in School of Electrical Engineering, so I was reasonably familiar. I used to be a teaching assistant in analog electronics, actually, in Belgrade. So.
Oh, wow. So see, I was just going to say, I've been doing digital for so long that actually sometimes I forget how much physics is actually involved in under the hood that we don't actually see day to day. And now that you brought this up about the limits of physics, for storage and whether or not you go magnetic or not. I mean, this makes me think how much of it is still happening without us, because we've become so specialized in what we do. I'm actually not even thinking about analog 90% of the time. It's just fascinating because when you're building these disks. So I just want to ask you a quick question related to hard drives. So, we've had hard drives for a long amount of time, right? For many, many years. When did since how much? Since when?
I think 60 years at least.
60 years.
I think the first RAMAC was shipped in mid-50s. So it's about 65 years, yeah.
So I'm going to come to some of the other questions, but just want to ask you this on the back of what you're talking. Since when did processors become important for storage? And what is the actual need for having better, faster processors for storage devices?
That's a great question. Processors are essential technology for storage, and in my current company that absorbed all these other storage companies, Western Digital, this has been recognized a long time ago. Western Digital used to have their own processor design, which they use for a variety of storage controllers that they were shipping. And they even at one point built a computer around their processor design.
Oh, right.
So as storage industry was evolving, originally the controller was a separate component from the actual storage element.
Correct.
The spinning disk was really just a bare bone servomechanical system with electrical connectors. The storage controller was typically a standalone device or part of the host, and this is how these things were organized, I think, in IBM originally. And Western Digital and several other companies started engaging in the storage controller business, which was fairly lucrative. And at one point, they had this great idea of integrating storage controller and mechanics together into a compact device that would expose a block interface to the host, which really started simplifying software stack. Because I don't know how much you remember early computers.
Yes, I do. Yeah.
There were, very often disk problems, and you had to do all sorts of host scanning and remapping of blocks, etc. So this caused quite a revolution, and the local processor, if you look at different tasks that it does today, it's overwhelming. I think the power of the processor complex on a modern enterprise hard disk drive or solid state disk drive actually eclipses the performance of laptops from 10 years ago. Meaning you have a very serious processing complex. You often have a very large memory, surprisingly large amount of memory. I forgot exact details, but gigabytes of DRAM.
Yes. That's right.
And powerful processor complex in terms of total of TOPS. You run it at a lower frequency because you want to control the power, but and operating system, very serious real-time operating system, custom OS, and employing multiple threads, etc.
So actually, when you started your career from physics, and you're talking about this physics dominated aspect and analog, now what you're saying is today's hard disks are much more dominated by digital, right? If you were to give a split of how much analog and digital in physics is being played out, what do you reckon?
Hard disk drives are amazing technology that way. I don't think that you can. I mean, it encompasses fundamental solid state physics and condensed matter physics of magnetism, of nanoscale magnetism, because bits today are only like maybe 10 nanometers in diameter. It encompasses incredible nanoscale hydrodynamics because the slider actually flies at the few nanometer fly height at the phenomenal speed, at a speed that's basically 30 meters per second. and with servomechanics that keeps that head with 3 sigma of like 7 nanometers or 8 nanometers, staying on the track, and with chemistry for the lubricant that keeps that interface lubricated, and with
make sure it doesn't get hot.
Yeah, with a pretty incredible analog channel, right, that operates at multi-gigahertz frequencies and does a signal conditioning and then error correction on that channel, mm-hmm. and then obviously the digital processor complex that puts all of this stuff together and abstracts it in a nice way to a user who just sees the LBAs, right? And never really has to worry, just use the right driver. And
Thank you so much for explaining this. So tell me, why are you working with the CHIPS Alliance? What is CHIPS Alliance anyways?
Great question. So CHIPS Alliance is a open source hardware effort that has naturally grown out of a group of open source hardware enthusiasts that originally met around RISC-V. We did not want to only have the open source instruction set architecture, but we got excited about the idea that microarchitectural implementation sitting behind this interface could be standardized in some interesting use cases. Mm-hmm. And we were thinking that basically there are several classes of embedded processors that everybody needs, and that the planet would definitely be excited to have a powerful out-of-order processing core, and that it would make sense to unite the efforts around the CPU in a similar way how software community got unified around the idea of standardized Linux operating system.
Okay, yeah.
So we basically wanted to make if you want to make an analogy, we wanted to make this, if RISC-V ISA was a mirror, mm-hmm. we wanted to make a mirror image of Linux kernel on the other side of the metal. And that was basically our original idea. So we formed the organization, and as we basically got created, we quickly started discovering all the important bits and pieces that are missing. Mm-hmm. And we had some great IP originally donated by Western Digital for RISC-V cores, but it was developed using proprietary tools.
Correct.
And proprietary tools kind of made it difficult to disseminate and share the design files, and especially verification test benches, because they were done with proprietary tools. And this has led to effort to sort of figure out, so what are the tools that we need to sort of start working on all this IP together? And the software and EDA component of the CHIPS Alliance just took off like crazy. And this is what happens with open, CHIPS Alliance is an open organization. Any company or individual can basically come in, and if they have a meaningful proposal, it can become a part of, the part of organization. So software and EDA component really started growing quite a lot, and interface architecture started growing quite a lot, because that's a second thing that's kind of fairly important.
You mean hardware interface?
How to build a common bridges.
Yeah. Right.
So now, 2 years after inception, we have several significant software projects in development of design tools and simulation tools. We have several exciting interface projects, like a chiplet interface and OmniExtend interface, mm-hmm. And we also have a original RISC-V IP donated by Western Digital and donated by UC Berkeley and from Rocket SoC. The list is long. You can find a couple of my presentations online.
Sure. So basically, you've created an ecosystem of open source software, EDA-based and hardware interfaces that can now be used on top of the original processor that Western Digital donated. But going forwards, what else would you be?
It's not. By the way, it's really not limited. You can
bring
can,
in
for
any
example,
other.
you can use the Chisel. So Chisel programming language and compiler are part of the CHIPS Alliance.
Right.
And you can use Chisel examples that came from Berkeley and Sci-Fi to design RISC-V processors.
Okay.
But nothing prevents you from using Chisel to design any other architecture, right? If you have a license for ARM or OpenPower, you can design that,
I see.
or you can come up with your own, or maybe you are just designing a DSP and there's so there's no limits. I think every component is based on Apache V2 license and basically can be used as is in any context.
So are you guys planning to then design more commercial grade processors with the intention of just open sourcing the actual design and the entire infrastructure of hardware around it? Is that the intent, that you would continue to make more and more processors, and would it be just available for free for anyone to use it? Is that the plan, or?
No, I don't think that necessarily all the processors designed by Western Digital would be open sourced.
No, but with the CHIPS Alliance effort.
We have in CHIPS Alliance, all the IP is
open source.
Open source,
obviously. Right.
Yeah, and yes, it's entirely possible that there will be new processing cores developed from the ground up in CHIPS Alliance, and we are in our core work group. We are sort of discussing those ideas as well.
Sure. Nice. So basically, what you're doing is you're killing the proprietary market of EDA effectively.
I don't think that it's being killed. It's really just it's probably going to create influences in the EDA market as well.
Yeah.
Basically, if we look at our most successful tool in CHIPS Alliance, we have a project where we are expanding Verilator compiler, and we are implementing System Verilog parser library together with Verilator in order to enable Verilator usage in universal verification methodology flows. And this is really what people want.
Yeah.
And interestingly, people want this because they want to have a UVM environment where all test benches and IP can be easily exchanged between partner companies.
Without being dependent on any particular tool from any vendor.
Yeah, so. And I expect that this will influence the industry and that it will basically, change how things are factored out so that people can do this. But also, if I look at the Verilator as a software package, all the companies that are using this code enjoyed the fact that it's open source, so they can understand it and maybe they can modify it, but they actually pay other companies for customer support. So nothing is really free. This is a genuine thing that we see with Verilator and with RISC-V IP from Western Digital. In case of RISC-V IP, CodeSIP has developed a business model where they basically maintain and improve open source cores in the CHIPS Alliance, but offer customer technical support and verification services around it.
Right.
And this is basically the best working model. And similar is the case with a couple of companies that are offering support and services in our Verilator. So I think that's really where the open source hardware and open source EDA tools are going. Yeah. I don't think that same as Linux did not kill Windows, right?
That's right.
It's simply and it's not that you can just download Linux source code and sell it to somebody. That's just not going to work out. You actually have to develop expertise and you have to offer a support and services, and then you can make a lot of money on Linux, as Red Hat has proven.
Yes, indeed. No, thank you for clarifying it. So it looks like going forwards, other than enabling better support for EDA, you'll also be introducing potentially new RISC-V IP that may be open sourced, and also the OmniExtend architecture, and obviously improvements and enhancements to that as well, right? So that would be my guess about the roadmap.
Yes. Yes, the OmniExtend is something very exciting. OmniExtend is a standard for putting cache coherence messages from the processing cores on the level 2 frames of Ethernet.
Right.
And that allows you building a compute clusters that utilize Ethernet IPs for the SoCs, Ethernet cables for the connectors, and Ethernet off-the-shelf Ethernet switches for the cache coherent switch. So you can sort of build large coherent CC-NUMA-like configurations by really repurposing very ubiquitous hardware that's very reasonably priced too.
So I remember seeing a demo that was in 2019 RISC-V Summit. Can't quite remember who was showing this. About chip to chip.
That was a demo with it was Sci-Fi who created the FPGA boards that supported tiling packaging over Ethernet, which is current version of OmniExtend.
Right.
It was Intel with Barefoot Networks.
That's right, Tofino.
Programmable switch.
Although
the architecture doesn't require, you don't need to have a programmable switch for this, but it's just exciting to do it as well, especially if you understand your cache coherence messages. And we had I think we demonstrated in 2019 we had 2 nodes. Last year I showed the demo on one of the conferences with 4 nodes, 4 cores each, and a switch.
Wow, that was really exciting. It was really exciting.
That's something exciting, and RISC-V is a new architecture. Obviously, some people may want to build cache coherence in some proprietary way to get the best performance for their specific use case.
Right.
But I'm kind of hopeful that for many companies who just want to sort of support this as an idea and especially enable interoperability, this can become exciting. One thing that's exciting is I can build a processor and you can build a processor, and we actually have a chance to share the memory in a coherent way.
This is sounding so exciting, but I'm just wondering, what about verification?
Of course.
I'm sure there are ways and means of overcoming those challenges. But
I say verification of cache coherence on its own is a art and a very special technology.
How on earth would that actually even happen? But I don't want to go too much in the verification side today. So I want to wrap up today with a quick question to you. Can you give us some tips especially for newbies? What should they be doing to carve out a successful career in engineering, whether it's electronics or software, if there is any such partition anymore? What would be your insight? What would be, you say, 5 things that everybody should do to become successful?
Well, it's difficult to create a prescription for success, because in my experience, especially as a manager and as a recruiter of new, fresh engineering blood for Western digital research and development, it really comes from your passion. So it's people who are very passionate about their work that they end up being very successful, and that passion actually is something that also enables them to cross the boundaries. So people who are very successful are usually not limited to one specific field, but also demonstrate that they are able to learn new subjects, new fields, and apply their skills in a new area. So I would say that the most important general prescriptions for success are actually having some passion for making new stuff, and then having this understanding that engineering career assumes continuous learning, meaning that you can't stop learning new things. You kind of have to have to learn new things, and as I have discovered for myself, you also often have to open old notebooks and and redo subjects you may have successfully passed 20 years ago. But,
absolutely.
You may want to do it again. Just say very much same fundamental thing. Yeah.
So what you're saying is something quite nice and precise. You're saying you're passionate about learning lots of new things, and you're also passionate about making new things. And so long as you're able to learn continuously and keep going back to the things that you may have learned and forgotten. And that's basically a whole closed loop control system, right? So basically that's the recipe for success. And that's quite true, actually.
Going to fundamentals is very important. I think algorithms beat programming languages and linear algebra beats Python.
And, in my time when I was at the university, we didn't have so much of internet education available, cool videos, opportunities to learn from experts. And I think these days we have that. And I think students should, exploit that to its fullest. Not everything is in a book. And even if it is in a book, having someone like you teaching them how a hard disk works from all angles in 2.5, 3 minutes of pitch could be a life-changing moment. Because, reading a book, where will you find a book that teaches you how hard drives work? This is the problem with education.
There is a book, actually.
Is it? Okay, that would be good to know.
Yeah. When IBM Malman and Research invited me for a job interview in 1999, I was kind of, first I was disappointed because I thought hard disk drive, it's like a gramophone. Why would I be interested like that? Because at Caltech we were already working on, I was working on gallium nitride high power devices, but my colleagues were working on memory, on silicon resistive tunneling diodes for memory errors. And so we were already thinking solid state memories. But then I read this book, before the interview. I spent like 5 days and crammed up and finished the book on hard disk drive.
So there is a book.
There is few books.
Oh, I see. So the book is called Magnetic Disk Drive Technology, Heads, Media, Channel Interfaces and Integration. Wow, quite a long title. And what is it? First edition, and the author is Kanuji Usher. Awesome. So let me wrap it for today. And thank you very much for coming in with me today. My listeners, I hope you liked today's podcast. And if you do, please let us know what you liked. If you want to hear more about anything particular, let me know. We'll be back next week.